Now I'd like to introduce Andrew Meyer, Director of Technology at Electric Cable Compounds Incorporated. Throughout his tenure in the wire and cable industry, his focus has been on material development of thermoset and thermoplastic compounds. Prior to joining Electric Cable Compounds, he held positions with the Merman Innovation Group and earned a degree in rubber engineering technology from Ferris State University.
Thank you, Mark, for the introduction. As Mark had said, my name is Andrew Meyer. I am the Director of Technology here at ECC. I've been with ECC about 2 years, been in the wire and cable industry almost a decade now. A little bit about ECC. We are custom and specialty compounded here in Naugatuck, Connecticut. We've been producing since 1988. We started really in the medium voltage industry space, and it's really the heart of what we do today. But we've really kind of branched out to low voltage markets and many other materials. Anything ranging from peroxide, irradiation, and moisture cross-linkable compounds, which is going to be what I'm going to be focusing on today. So we'll get into it. We're going to talk a little bit about the EPR, moisture cross-linkable technologies, give some application examples, some challenges, and go from there. To start out, and sometimes it's going to be a little bit of a delay between me switching slides. So if I pause for a second, just waiting for the slide to catch up. So to start, we'll go over an overview of moisture cure technologies, how it is really ran a lot of the systems we see today, and then kind of go from there. So in a moisture cure technology, you have a grafted base and in general a catalyst master batch or a flame retardant master batch that is combined in a thermoplastic extruder. It's mixed, homogenized, put on the wire, and then usually it sees moisture, whether that moisture is just in the water trough, if you're placing it in a sauna, or underneath a water tank. The system cross-links and is thermoset.
Hey, Andrew, this is Chuck. Can you switch your display settings? We're seeing your regular presentation speaker module. Under display settings up there, you can switch the screen. There you go. Perfect. Thank you.
Good. You can see the presentation right now?
Yep, you're all good.
Okay, thank you. So, the moisture cure technology is really a way to achieve a thermoset material without heavy capital investment of either a CV line or electron beam irradiation. And, there's really not a whole lot of equipment necessary to do that. So you get a lot of the benefits associated with thermoset polymer without having to, invest heavily in the capital side. So there's a pretty low barrier of entry. Most people have thermoplastic extrusion lines, which is really, a majority of what's required when it comes to extruding the systems. Some of the other equipment that is necessary, or at least would be recommended, not necessary, I would recommend a gravimetric feeder system. So the top right photo here is of some Meyer gravimetric blenders. Now there are a lot of different gravimetric blender systems out there. I just kind of put together this presentation. We just happened to choose Meyer. That's some nice photos. But there are a lot of other manufacturers out there. So the top right photo is a couple gravimetric blender systems. And this allows for the proper ratios to be blended in and fed into the extruder in the correct manner, where you're not getting any settling or separation of the base to the catalyst master batch or flame retardant master batch systems. The other thing that is really nice to have is a dryer. Now, in winter months, sometimes the dryer, you can get away with it because the humidity in the atmosphere is fairly low. When it comes to the summer months, and especially up around us right now, it is pretty hot and humid around here. So a dryer in most cases is really necessary. Drying of the catalyst certainly helps with the extrusion. It stops a lot of the scorchinesses that can come from having too much moisture in some of these materials. That is one of the challenges we'll talk about a little bit later on. There's a couple of photos of dryer systems in the bottom half there. Another good way to monitor moisture content is dew point monitors within the systems. For our systems, they're all pelletizable systems. So you throw them in these dryers, whether it's a desiccant-based dryer or a vacuum-style dryer or just a hot air bed. You really want to make sure that you get the moisture out of the catalyst system in order to help with the extrusion and make sure that scorch does not occur in the extruder itself. Another thing that I would say is not necessarily needed, but is applicable in certain moisture-cure systems is either a sauna or a water bath of type. We've seen it before where sometimes there's some pretty inexpensive options where they'll take an old shipping container and basically pipe in a steam generator. You'll roll the reels in, and then after just pump in steam, 150 F for either a few hours, a couple of days. It really depends on, the time, the temperature, and the thickness of what you're trying to cure. And that is just if you're really trying to force cure the systems. There are ambiently cure systems where basically you'll extrude the wire, you'll let it sit on the reel, and then anywhere from a few days to a couple of weeks after, that system naturally cross-links, and you have a final product at the end. One other piece of equipment that I do kind of recommend when it comes to the system is a hot cleave test set. And this is really just to understand how well you've cross-linked the system and determine if it's fully cross-linked within a certain time frame or not. And I'll actually show a photo of that later on. But from a capital intensity side, it's pretty low when compared to a few $1 million of a CV or even electron radiation. So there is a low barrier of entry when it comes to capital investment, certainly. Benefits and attributes of EPR. So, why talk about EPR? What makes it unique? So EPR is ethylene propylene rubber. The building blocks are pretty basic when it comes to it. It's ethylene is attributed to XLPE. So what makes EPR different? Well, it's flexible for one point. Most cases, EPR is pretty amorphous polymer. So you get a lot of the flexibility. You're not giving up a whole lot of the performance to get that either. They are still very thermally stable systems. They're systems rated up to 150 C and beyond. They have a versatility of unlike any polymer, it can be used many different places and in many different types of applications. Its processability is generally very good. These are pretty easy polymers to process. They don't have very high melt points. They don't have issues with compatibility of systems for most cases. And then basically you can extrude them on a very large range of equipment. The other benefit to EPR is the cross-link densities of these systems. Compared to an XLPE system, the cross-link density is huge. It's really a very active system, so it has a lot of sites that are allowing it to cross-link versus that of, say, an XLPE moisture cure. One of the benefits of moisture cure EPR is that it is a thermoplastic extrudable system that cross-links and is almost a direct comparison to that of the CV-based conventional rubber systems. Talk about some of the application examples that are utilized in moisture cross-linkable EPR. All of our systems are of pellets. They do lend themselves to a wide range of equipment. The automotive side, there are a lot of systems that use moisture cross-linkable. Certain standards, SAE 1127, 1128, ISO 6722, 194, 642. There are applications that are used moisture cross-linkable EPRs. AWM styles, we see a lot up to 150 degrees C rated. Photovoltaic systems, we see them used, any VW1 rated systems as well, UL 4703. Industrial type applications, we see a lot of robotic type of systems. Transit applications is another one that tends to see a little bit of usage when it comes to the moisture cross-linkable EPR systems, and UL 44 type applications where we have XHHW 2 rated systems, whether it's FT2, VW1. So it really kind of shows the versatility of these systems out there. They have pretty wide range of scopes. You can see them in some of the military applications. It's pretty versatile. There are a lot that can be used in. And when it comes to the base system, there are a lot of different master batches that are available out there that can really tailor those systems to whether it's an automotive application, whether it's an AWM application, UL 44 type. So really it's just the use of a base master batch, and you can go into particular markets. So you could actually have one singular base, be able to utilize that with several different master batches, and you could be in 3 or 4 different application spaces with basically one singular master batch and base. So what are some of the challenges associated with moisture cross-linkable systems? It's a little bit harder when it comes to the handling requirements, right? There are multiple components, not just, hey, we're putting one system into the back of the extruder, we're getting one system out at the other end. Obviously, there are, a couple different components that you need to have, at least a base and a master batch component, or a catalyst master batch, or FR master batch, depending on what you're looking to achieve. And obviously, you need to homogenize those correctly. They need to be weighed up correctly. They need to be fed correctly. So there's a little bit of a handling challenge when it comes to that. The second challenge tends to be shelf life. These systems have a finite life, and they can't just sit on the shelf for 2-3 years before use, right? Whether it's 6 months to a year, or perhaps longer, depending on how these systems are stored. But there is a finite life to these systems, so you have to utilize them within a certain period of time, and to get the correct properties. Another little bit of a challenge, and depends on kind of how you look at it, is the delayed quality assurance due to the cure time. So as I described earlier, was the hot creep test. The photo on the right actually depicts the test being performed. So the hot creep test is actually it's a hot test where you're exposing the sample to 150 degrees Celsius under 29 pounds of force for 15 minutes, and you're actually taking a 1-inch benchmark. After the 15 minutes, you're looking at how far that sample elongates, and that'll give you a percent of elongation. After the 15 minutes, you will remove the weight and see how much that sample shrinks back. And what this tells us is actually the level of crosslink in the system. Now, EPR systems are very tight compared to XLP systems, so they crosslink very good. The troubling part is that sometimes you have to wait for the quality assurance aspect. Obviously, if you're extruding a CV product, it becomes cross-linked, and by the time it hits the end of the tube, it's ready to go. It's cross-linked, and you just have to do your quality assurance at that point in time. Same with electron irradiation. You extrude the cable, and then you have to take it to a secondary operation, and then you can check it right after it comes out of the beam. With moisture cross-linkable systems, you extrude, and then you either have to wait the ambient cure time, which could be anywhere from a few days to a couple weeks, depending. And in certain applications, this is acceptable. And then you can just check it over a period of time and then understand what your cross-link density is. Or you can force cure the systems, which can be done in a couple hours to a day or two. And so there is a little bit of a waiting period associated with that. But generally from the crosslink perspective, they all kind of get to the same point. But it is a little bit of a challenge, especially if you're running into time frame constraints. But certainly it is something that is overcome, or able to overcome. Its performance certainly versus conventional materials is comparable in many applications. really is just, a different method to get there, whether it's, the moisture cross-linkable, whether it's CV or electron radiation. They all kind of get to the same place once it gets to the cross-link, that's necessary to achieve the performance. It's really just the way you get to that point. The cure times typically, I would say, are just a few days in most cases. In ambient, depending on wall thickness, you can see them up to a week, 2 weeks, depending if it's a really, really heavy wall, about 100 thousandths. It can take a couple weeks to get there if you're looking ambient. Now, that same system in a force cured, could be 24 hours at say 150 with high humidity in a sauna. So it's challenges that are pretty easy to overcome, and most manufacturers have the equipment necessary to handle that. In summary, I would say that EPR, moisture cross-linkable products, allow manufacturers a lot of flexibility to provide a thermoset cable construction without the heavy capital investment of a CV or electron beam or radiation unit. These systems are used across the board in all the same markets and applications that you see the CV and electron beam or radiation cross-linking units out there today. So it's pretty flexible product. There are a lot of different applications that it can go into, and it's certainly something that's coming to become more popular over time.
Thank you, Andrew, for your presentation. Several questions have come in. I'd like to get to them. What is the minimum moisture level a compound should have to avoid problems in the process?
I would try to maintain below 0.2% moisture content in all components.
Okay. Are lubricants or mold release chemicals used in the master batch to help with feedability in the extruder?
Lubricants. I would say no.
Okay. And is there a minimum wall thickness that EPR is capable of?
We've seen, I can only speak to our product lines, but I would say I've seen it down to 15 mils, 10 to 15 mils we've extruded.
Okay. Transit applications were mentioned. Are these materials considered to have low smoke generation?
Yes, in a lot of the applications we've seen, we've passed, even in non-FR systems, ASTM E662 testing.
Okay. And also automotive applications were mentioned. Have these materials been considered for hybrid or electric vehicles?
Yes, they have. A lot of the EV requirements conform to UL 62, and these applications will meet that requirement.
Okay. In terms of customers, which sectors have posed you the most challenging technical, are the most technically challenging for you, or can be, I should say?
The automotive sectors can be quite difficult, especially with some of their longer-term heat aging requirements. So, that has been a little bit of a challenge to overcome. The UL 44 market space tends to be a little bit difficult upon the requirements to meet the XHHW -2. So that is also a little bit of a challenge as well. But certainly we've overcome a lot of that.
How closely do you follow all the potential codes coming down the pike for your customers? Or how involved are you in preparation internally for what may have to come for your customers?
We certainly try to be up to date when it comes to standard changes or any new standards that are introduced to the market space as best we can. We try to work through our customers, understand what their knowledge is. There are a lot of our customers that do sit on the panels or the boards when they are developing these standards. So we try to be as close to the ground floor as we possibly can in understanding any changes that come to fruition with any of the standards.
Yeah. You talked earlier about some equipment like dryers and blenders. When it comes to that internally, does the company try to stick to one OEM because it's easier to, everyone's familiar with a given company, or do you consider or use multiple different brands?
We have seen many different brands. We don't have any internal dryers outside of what we use for our manufacturing process, but a lot of our customers have their specific manufacturer that they like to use. And so we've seen many different operations where they have a bunch of different dryer sets, and all of it works as long as you get to the same point, which is drying the material. So
Okay.
in most cases, if you can use a dew point monitor to really understand where your moisture content is, that helps. And it can be achieved in various different dryers, whether it's a vacuum dryer, desiccant bed, or just a hot air dryer.
Okay. To your knowledge, are there wire automotives using EP moisture curable to manufacture their cables?
Yes.
Is that rare or is that common, or?
I would say we've seen more inquiries nowadays than we have. It's becoming a little more popular.
Okay. Is it possible to make EPR insulated medium voltage power cables by using moisture curable EPR system similar to the moisture curable XLPE?
It is possible. The challenge that we see is not necessarily from the insulation side of the fence, but actually from the semiconductive materials necessary. I don't know of any semiconductive moisture cross-linkable semiconductive materials currently, and so the challenge is not necessarily with the insulation. The insulation materials are certainly capable of meeting the requirements. It's the semiconductor insulation shield and conductor shields that are kind of lacking right now.
How widely do you export? For instance, do you export to Brazil? And when you do you have to test versus IEC specs?
So yes, we do export materials, and yes, a lot of the times it depends on the manufacturer and the standards associated. But we have seen IEC specifications. We can meet some of the IEC specifications from the standards associated with various other industry marketplace standards.
Okay. And what is the maximum voltage you could recommend to apply EPA moisture curable?
That's kind of a tough question to ask. I would say if we understand more of the cable construction, right, because it's necessarily the voltage stress associated with the cable, not necessarily just the material capabilities. So, I would say if we want to talk a little more detail, then I can maybe answer it in, a little bit better.
Okay. And let's see. Oh, is there a recommended profile for extrusion?
It depends on the grade of material, certainly, but generally we're 350 degrees up on the head or below, and then you just kind of step it backwards from there.
Okay. In terms of your customers in general, is there any one area where there's likely to be misunderstanding of the nuances, that something you have to deal with customers on a regular basis that you could address?
I would say a lot of the times we tend to run into a lot of customers that are used to running XLPE and are kind of used to that XLPE mentality, where the temperatures are a little bit in excess of where you maybe want to run with the EPR systems. So a lot of it's just retraining to try to understand that EPR systems are different than that of XLPE, and as such need to be treated different.
Okay. What about the shelf life of your products? Does it range a lot depending on the product?
Our 6 months to a year, depending on how active the systems are, or we've seen them go certainly beyond that, depending if the the foil liner, for example, that these systems in are kept in a good shape, if they're stored correctly. So in most cases it's a year, but sometimes it can be a little bit beyond that, depending.
Okay. Would you recommend using EPR moisture curable compounds in mining cables against ICEA and CSA standards?
It again depends on cable construction. So I would say, if we want to talk a little more details, we can talk offline about that.
Okay. What are the challenges with using EPR as an alternative of straight silicone rubber?
I think you need to get into more of the application, what you're looking to do with it. Again, I think we should talk more details, maybe offline, on what you're looking to understand there.
Okay. In terms of linear speeds, how fast can EP moisture curable material be able to be run at?
The fastest I have seen in some of our trial sets is about 2,000 foot a minute.
Okay. And I think we have time for one last question. And this was a multi-part. What are the typical extrusion processing conditions recommended for a single screw extruder?
What we'd recommend is, you're going to want a mixing screw, something that's not necessarily shear intensive. You really just want to homogenize the mix, but you don't want to overly shear it because of the scorch issues that can occur. So either but what we have seen, I should say that we have seen barrier screws, we've seen barrier spiromatic screws work. So, these higher shear intensity screws do work in homogenizing the system. You just need to take a little more care in the temperature profiles. Like I said, the temperature profiles could be up to 350 degrees Fahrenheit. Generally, we start a little bit lower than that and then just kind of work our way back to, say, 280 in the back end.
Okay. And if catalyst master batch is dried, how prevalent is scorch?
Can you say that one more time, Mark?
If a master batch is dried, a catalyst master batch, how likely is it you end up having a scorch issue?
I would say then it depends a lot on the temperatures and your setup that could then correlate to how much scorch you would see. But certainly I would recommend drying the materials. It does allow for a much larger process window. When you have more of that moisture in that system, it just makes it more susceptible to beginning the cross-linking process.
Okay. Thank you, Andrew, for a great presentation. And at this point, I'd like to ask Dane Armendariz to continue with the next segment.